Welcome to this video. In this video, I will be talking about min-conditional entropy and the semi-definite program of min-conditional entropy. So, min-conditional entropy plays a crucial role in quantum cryptography, particularly, and it can be related to quantum correlations and entanglement via this semi-definite programming, and we will see how it goes. So the idea of semi-definite program is that it is a subclass of conic programs. So I have written here, it is a subclass of conic programming which is efficiently simulated by classical computers, and there is reasonable accuracy in the output. So these are just words and some motivation. The idea is that in conic programming we have some optimization problem. So we have an optimization problem, and this is specified by a linear map lambda and some coefficients a and b. So these are constants for a given problem, and for semi-definite programming and using min-conditional entropy, we will see that what these constants are, how we can determine them for a given problem. So given these tuple, this tuple. So given this tuple lambda a and b, we can define primal feasible set and the dual feasible set. So the primal feasible set is such that I have written here lambda of x is a, and x belongs to some cone, convex, closed convex cone, and the dual feasible set is such that the main constraint of the dual problem, which is belonging to k star, this particular constraint is represented by the dual feasible set, basically. So it is all those y's which within which the dual optimizing value will be attained. So this is the idea. And the primal problem I have written here, primal and the dual problem both for conic programming. So this side is conic programming, and that other side is basically the primal dual problem for HDP program, so semi-definite program. So from going from conic programming, if you take the closed convex cone as the set of positive semi-definite matrices, and your vector spaces over which the linear map acts are Hermitian matrices, set of Hermitian matrices over the reals, then we define the primal problem and the dual problem in this particular fashion. So this is the primal problem and this is the dual problem, and this side is what is called as HDP. So it is just a particular case of conic programming where the cone is the set of positive semi-definite matrices, and we have linear map acting between set of Hermitian matrices, so which is a vector space. And now with this we will move on to the idea of weak duality. So the primal problem and the dual problem that I have talked here, they are actually kind of the minimization and maximization has been interchanged compared to what I was discussing before. So the weak duality in this case is that the primal value, the optimal primal value is always less than equal to the the value of the dual problem. So this can be easily seen by taking any x belonging to the primal feasible set and a y belonging to a dual feasible set, and then using the definition that the dual feasible set satisfies this constraint because it is a dual cone, it belongs to a dual cone. So lambda star y minus a inner product with x is always greater than equal to 0, and this gives you the bound that any y inner product with b, this is the optimization of dual problem, and this is always upper bounded by the optimization of the primal problem, and that's the main idea. Now let's come to the discussion of min-conditional entropy. So min-conditional entropy has a definition of this form. So this is the definition. So 2 power minus h min. So why it is 2 power? It is because otherwise you will have a log in the definition everywhere, which is just added level of complexity. So to keep things simple, I am using 2 power min-conditional entropy of a given b for a state omega ab. So omega ab is the state, And mean conditional entropy of this state is given in terms of infimum over tau b greater than equal to 0, and you calculate the trace of tau b, which is a positive semi-definite operator, and subjected to this operator inequality that identity tensor tau b is always greater than equal to my state at hand. So it is the minimum amount of noise in form of this state such that this inequality is satisfied. Now we can cast this in a nice way in the form of dual problem. So here again, instead of infimum I am using minimum, but infimum will also be fine. So here I have minimum over trace I times y. So here y is playing the role of tau b, and I have this minimum such that phi star yb minus my state is greater than equal to 0, and now I must represent this condition, this inequality here. And to represent this, I use the definition of phi star as the follows. So phi star of yb is I identity on the A space tensor yb. So this gives us a map phi. This I will discuss. So once I have this, I also have y belonging to the Hermitian matrix. Now y belonging to the Hermitian matrix is a weaker condition than tau b greater than equal to 0 or yb greater than equal to 0. But the point to note here is that I have two constraints. The first constraint is I tensor y minus omega is greater than equal to 0. This constraint for all omega, it means that it is always a positive semi-definite matrix. This is because like suppose you take a fixed omega, the omega is in turn greater than equal to 0, and I tensor yb greater than equal to 0 means yb is a positive semi-definite matrix. So with this I have the dual problem. So I have the dual problem here, and in this problem what is A? A is my state omega AB, B is identity, and phi is just a partial tracing. So partial tracing is a linear map and phi is exactly that. So it is partial tracing of trace A. So partial tracing of system A. So now one thing you can notice is that my operation of partial tracing, if I take the adjoint of that operation, it is exactly the phi star the way I defined here. So this is clarified in the box. So in this box, if you look carefully, you will find the reason why the adjoint works the way. Now with this as a dual problem, we can frame the primal problem also, and that I have framed in here under the heading of primal problem. And the primal problem is maximization over my state times a matrix which is belonging to AB space such that phi of x is identity. So identity comes from the fact that my B is identity, this fact here, and my x AB is greater than equal to 0. So this I am just using the primal and the dual problem of the SDP form here. You can check easily and framing the primal and dual problem. And now the idea is to discuss a bit on strong duality. So I have a primal problem, I have a dual problem, and it is easy to see that the set of primal feasible set, it is not empty because IAB belongs to the set. So if you take IAB as X, then what you can see is that IAB identity on AB space is such that if you trace out the A part, it is identity on B, and identity on AB is always positive semi-definite. So my set A, which is primal feasible set, it is non-empty. It is not equal to the empty set phi. And the second point is that the dual feasible set is also non-empty, and it has a element contained inside it rather than on the boundary. So this is given by the fact that you can take the maximum value of your state in question, and you can add to it a small positive number which is greater than equal to 0, and this will give you IA tensor YB as strictly greater than 0. So this is a strict inequality, strict. But you can see that in the dual problem we needed only a loose kind of a loose inequality, but the strictness guarantees that the dual feasible set has a relative interior inside it. So this idea of relative interior we will look into detail when we talk about strong duality. And the point is these arguments show that the primal and dual problem are same. So this set A being non-empty and set B being having a relative interior so shows this kind of thing. So with this idea we can now say the primal problem can be massaged in a particular way. So the primal problem is maximization over this inner product subjected to xb is identity and x is greater than equal to 0. So now there is an isomorphism in the space which I will discuss. So the isomorphism is that let's talk about the isomorphism first. The isomorphism is that a matrix such that whose trace on A part gives you an identity on B and the matrix is positive semi-definite is isomorphic to a map like Choi isomorphism to a map which is completely positive, that is this part which is completely positive, and unital, basically it preserves the identity matrix. So this is different, it is not completely positive trace preserving, rather it is completely positive and unital. So this epsilon prime is completely positive unital map, and I have to maximize over all these maps, and I can drag this here by an adjoint. So this is just epsilon prime adjoint, and the adjoint of completely positive unital map is a completely positive trace preserving map. So this is CPTP. This I will discuss shortly, but the idea is now min conditional entropy in this fashion. If you look into this box, it can be written as supremum over all CPTP maps such that you locally apply the map on B part of your system AB and you check when the overlap is maximum with a maximally entangled state. So this is kind of looking into it from the lens of correlation such that you are locally applying on the system a map that maximizes the correlation basically. So this is called sometimes the singlet fraction, and you have to maximize the singlet fraction using local operation. So now let's look into some important points regarding the isomorphism. So the isomorphism is that if you have a CPTP map, it is isomorphic to a operator that is positive semi-definite and whose trace on B part gives you identity on A. So this condition is of trace preserving and this condition is of complete positivity. And this is the Choi isomorphism or Choi-Jamiolsky isomorphism. And similarly, there is another idea which is you have a completely positive unital map, then it is isomorphic to an positive semi-definite operator. So this is CP condition such that trace on A part is identity on B. So this is the unital condition. So IB, and this is the unital condition. So why is this unital condition? You can quickly check. So I have written here. So if you go down this arrow, you can see that this is what you will get if you take phi as summation over I. And now if you trace out the A part, you get something like this, which must be identity. And this means that by linearity of this map, this epsilon is a linear map, you get this constraint that epsilon of identity on A is identity on B. So with this, it clears up the point that a completely positive unital map and a completely positive trace preserving map are different, and in particular they are adjoint of each other. This is because if you have a completely positive unital map, then it will have some cross operators that satisfy this, such because epsilon prime of identity is identity, which implies that summation over I ki identity ki dagger is identity, and that is this condition here. And if you take the adjoint, it is like taking Hermitian conjugate of each of the cross operators, and this gives us a new operator that is ei. Now ei dagger ei is identity. So this is the condition of trace preserving in case of CPTP maps. So this is the main idea, that adjoint of a completely positive unital map is a CPTP map, and this is what we used in this to say that min conditional entropy, rather the 2 power minus min conditional entropy is of the form that it is maximum over all CPTP map on party B such that the singlet fraction is maximized. So with this I end my video. Thank you. In the next video I will be talking about some quantum algorithms, particularly Grover algorithm. So let's see how it goes.